Fluid Notes, Part 1. Density is defined as mass divided by the volume. This is the symbol we use for density is the Greek letter rho, as in row your boat. Now we use this formula quite often. Usually what we're doing is instead of calculating the density is something that's known, we use it to calculate the mass. So multiply both sides by V, we get the mass is the density times the volume. Density in physics is measured in kilograms per cubic meter. Density of water is something you should have memorized. It's 1 gram per cubic centimeter in chemistry class. In physics, it's 1,000 kilograms per cubic meter. Pressure is defined as force divided by area. It's measured in pascals. Pascal is a Newton per square meter. Newton is for force, square meter is for area. Pressure in fluids. Pressure increases with depth. So I have an object I'm pushing down in the water. The deeper I go, the more pressure there is. We calculate the pressure with the density times gravity times the height. And the height is actually the depth, how far under the surface of the water it is. So rho GH is formula for underwater pressure. Remember that pressure is force divided by area. So I could calculate the force by multiplying the pressure times the area. As we go down, the pressure increases and therefore the force also increases. Here's an example of that. The pressure down at the bottom of this object is rho GH, and the pressure at the top is rho GH. So this difference in the heights is causing a difference in the pressures. We have a higher pressure at the bottom, a lower pressure at the top, and that's going to cause a pushing force upwards. Now if I multiply this pressure times the area, the surface area on the top and the bottom of the object are the same. So we get a force on the top and a force on the bottom. There's a higher force on the bottom, and that makes a net force going upwards. We call that net force the buoyant force. It's the difference in force between the top and the bottom objects. So substituting rho GH times the area for each one of these, I can factor out rho is the same, we're in water, gravity is the same, and the area was the same on the top and the bottom of my object. So factoring those out, then we have H1 minus H2 in the parentheses. And I know area times height is the volume. So this formula becomes rho GV is the formula for the buoyant force. And we have to be very careful with our definitions. The rho is the density of the liquid, which would be water, and the V would be the volume of the object that's in the water, and it's only the part that's underwater. We don't count the part of the volume that's above water. All right, here's an example. I'm holding a log under the water, 24 kilogram log, and we got a volume of 0.02 cubic meters, sink or float. So there's two forces on it. The buoyant force pushes upwards and the gravity force pulls downwards. So we have to calculate each one. The buoyant force is rho GV. So density of water is 1,000 kilograms per cubic meter times gravity times my volume, 0.02 cubic meters. Comes out to 196 newtons. Right, force of gravity, m times g, comes out to 235. So the larger force is the force of gravity, so the log will be moving and accelerating downwards. This difference between these two forces is called the apparent weight. We're subtracting the buoyant force from your weight force, and that difference is your apparent weight. If you've ever been in a swimming pool, you realize that you weigh less inside the water than out, and that's because the buoyant force is pushing you up. In this case, it comes out to 39 newtons is your apparent weight. Now, if we look at something that floats, like a ping pong ball, when it's under the water, the buoyant force is larger than the gravity force, and that's going to make it accelerate upwards towards the top. However, when it gets to the top, it stops moving, and that tells us that these forces are now balanced with each other. Now, the buoyant force is rho GV, and the V is the volume that's underwater. So when it was down here, the entire thing was underwater. Right now, we just have this little bitty piece right here that's underwater, and that has decreased the buoyant force because this volume that's underwater has decreased until a point where these two balance with each other. So when an object is floating, the buoyant force is equal to the weight of the object, or the force of gravity. Our apparent weight ends up being 0 because the difference between two things that are equal would be 0. So for an object that's floating, the apparent weight is 0, and that means the buoyant force is equal to the weight of the object itself. Now that's only when it's floating. If you push the object under, volume underneath increases, and that increases the buoyant force. Archimedes' principle says the buoyant force is equal to the weight of the water that the object displaces. It also happens to be equal to the weight of the object itself if the object is floating. So let's look at this. This is the buoyant force, and this is the weight of the water that's displaced. So I will substitute rho GV for the buoyant force and m times g for the weight of the water. So this would be the mass of the water here. Remember that this volume is the volume that's underwater. It's not the entire volume of the object. And then this is the mass of the water that is displaced. That it's that same volume of water because this volume is displacing this mass. So if the object's floating, this is also equal to the weight of the box, which would equal m times g for the box. So looking at a diagram here, this is the part that's underwater. So this volume right here is the volume in the rho GV formula. And that is the amount of water that we're talking about. The weight of this much water is equal to this buoyant force. All right, so the buoyant force equals the weight of the box itself. And we're going to use my density substitution. I can calculate the mass of that box by the density of the box times the volume of the box. Now this volume is the volume of the entire box, while this volume is the part that's just underwater. So we can use this relationship then. Notice that the g is going to cancel on both sides. We can use this relationship to figure out when you put something in water how deep it floats in the water, how much is underwater, how much is above water. So we use this ratio, the density of the object divided by the density of water, or the volume of the box that's under the water, that's the volume of the water that's displaced, divided by the volume of the entire box. So this tells us the fraction of the box that's underwater. This example came from the old textbook. It's not really useful, but we can explain it here. Archimedes' principle used to be used to measure the density or specific gravity of an object. Specifically gold, they were able to tell if something's pure gold by submerging it in water, and you weigh it outside of the water and inside of the water. And we can use that same relationship to calculate the density of the crown, using the density of the water and the weight of the crown before and the change in the weight after when it's in the water. All right, our next topic is water pressure. We've talked about this before. The higher your water tower is, the more pressure there is, because the longer this h is, the higher the pressure gets. Pressure is rho g times that height. How high is this column of water? So I can calculate this. This is the density of the water, gravity, and we have a height of 30 meters. And that comes out to 2.9 times 10 to the 5 pascals. And you should recognize 10 to the 5 pascals is also an atmosphere. So this is 2.9 atmospheres. Now when we're considering something like this, not only is there pressure coming from the water, but there's also air pressure above it. In this case, we're going to assume that the air pressure at the open faucet is equal to or about equal to the air pressure up at the top, so they're going to cancel each other out. But what that means is when I turn the faucet off, the pressure inside this pipe is not only the pressure from all of this water, but also the atmospheric pressure pushing on the top of this. This concept is called absolute pressure. How much pressure is down at the bottom of the swimming pool? The absolute pressure is the pressure at the bottom of the pool plus the air pressure of all the air that's above this. So the rho GH is coming from the water that's above the object, and the atmospheric pressure is coming from 15 miles of air that's above the object. This one's called the gauge pressure. When you're measuring the pressure, like at the bottom of the pool or the bottom of a beaker, it's called the gauge pressure. And we use the symbol P0 for the atmospheric pressure. Pascal's principle, when pressure is applied to a fluid, the pressure is equal throughout the fluid. It stays constant all the way through. We'll talk a little bit more about that tomorrow, but the pressure in equals the pressure out. So this diagram here is a diagram of like a floor jack for lifting your car. The side that you're pushing on has a small area, so you're pushing with a small force, and that pressure stays constant all the way through the fluid, and that pressure pushes on a larger area over here, which creates a larger force on this side. Remember, pressure is force divided by area, so we have F in over A in equals F out over A out, and then we can use this relationship to calculate how much force we need to push to lift a particular object. This example of a jack lifting a car, then, we have the two different areas. If I divide these numbers, we find out that this surface area of this piston is 20 times larger than this, and that means we're going to push with 20 times less force. Rather than thinking of it as a ratio like that, we just actually use the formula and solve it for the input force, and it comes out to be 125 newtons. End of notes.